Welcome to the Cosmic Pie Podcast, episode 26, season number 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota. We are trying out, even now, some additional new software. Robert, do you think we'll pass the muster this time or what?
It's hard to say. I hope so. We keep tinkering with things, finding out new things. Sooner or later, one of our ways has got to work. In fact, it is imperative that we figure out how to make it work. But going back down into the musty basement and having both of us end up with migraines to do the podcast is not going to work.
Not at all. Now, just to remind people that we do have a chat feature that is running. If you have any comments or questions, feel free to use that. We have a question already. Extrabola is asking, what software are you using? We are using OBS to stream to YouTube, and we are connecting between us using Video Ninja. And and for those of you who are interested in doing your own podcasts in the future and using this type of software, one of the things you have to watch out for is the resources that your computer can handle. You really need to have a good graphics card and with lots of RAM and also CPU and RAM in the computer itself. And the other thing we run into issues is the USB connections. There needs to be a lot of those that can run both the bandwidth and the power for them.
Yeah.
So there are a lot of things to consider.
Because believe it or not, you end up having to have more than one mic. You have to have more than one camera and just a whole plethora of things going on. So
definitely. Now, the other thing to remind people is we do upload our podcast the next day on Spotify. So if you'd like to watch us on that platform, feel free to do so. And also don't forget, give us a thumbs up or subscribe if you haven't subscribed. And Robert, do you want to start off things by doing the disclaimer so we don't get fired?
Aren't we a little too late? Okay, all right. The views and opinions and everything expressed herein are those of myself and Wayne. They are not the views of the University of North Dakota, the Department of Arts and Sciences, or the School of Arts, College of Arts and Sciences, or the Department of Physics and Astrophysics here at UND. It's just us. We're the crazy people you have to come after.
Yeah, and someone asked about Spotify. We're under the Cosmic Pie, so I can't remember the full address, Cosmic Pie _UND or something like that. I'll look that up later and make a mention of that maybe next time.
We can put it in the description later on.
Yeah, exactly. I'll put it in the description later so everybody get that. And we're also on Instagram as well. So maybe I'll put that handle on Instagram, then you can find us and hopefully follow us on there. So we can do all those things for you later. But to start things off, let's do this. Let us introduce our guest coming up next Tuesday. So I'm very excited for this. So Dr. Seth Shostak, who is a senior astronomer and the director of the Center for SETI Research. He works at the SETI Institute in California. He will be our guest on Tuesday, August the 4th, same great time, 5 p.m. Central Daylight Time. And Seth is one of those sort of outreach type of people who's been on a ton of podcasts and radio shows for decades. In fact, I think I first heard him way back somewhere in the mid-1990s. He was on the Coast to Coast AM with Art Bell, and he was been on there several times since that time. And he is the real-life Jodie Foster, if you think of the movie Contact. I mean, he's involved with trying to find signals, is predominantly what they look for, in the radio coming from, advanced civilizations that are maybe broadcasting either purposefully or accidentally out into space, and we happen to intercept those transmissions. So his big thing, of course, is to try to figure out different ways, especially nowadays with the advanced computer techniques that we have and algorithms like AI, is how do you use that to look for signals that otherwise may be very difficult to find, and amongst the noise of the background hiss in the radio, that represents our galaxy and beyond. And so he should be able to provide us a lot of good insights into all this type of work.
Yeah, I've had I for those of you who don't know, I've been a volunteer with the space track at DragonCon, and we had him join us there 1 year, and all of our interactions were really good, really great. So he's a good gentleman. So
Yeah,
yeah.
so lots to talk about, definitely,
Mm-hmm.
for that. So that's next Tuesday, just to put another plug in there for next week. Now, the big news item for this week, of course, is something we were looking forward to for several weeks in a row, and that was the launch of Starship Flight Number 13, and that finally got off the ground last week. In more ways than one, it was a much more successful flight than Flight Number 12, and we'll give you some interesting slides that go with that. It's always kind of breathtaking when you see this thing go up. It's like 32 or so engines in the first stage. It's like the only people that used to have that was like the Soviet Union at the time,
Right.
back in the day, right? They
Yeah.
seem to go like the trend of not having super large single rocket engines. If you think of like the F1, I think that produced 1.5 million pounds of thrust. Then there was five of
Yeah.
them in the first stage of the Saturn V, the vehicle that took us to the moon. And the Soviet Union didn't do that. They had smaller engines, but they had a whole bunch of them. It was a big, large cluster of these engines.
And they demonstrated several times why that's not always a good option, because if they don't fire in sequence and all together, the rocket falls over and explodes. Uh,
And, and of course, there's an advantage to it.
mm-hmm.
And that advantage would be the fact that if one of the engines fail and shuts down, it's not catastrophic.
Right.
So you build in that redundancy, which allows you to operate the rocket on a couple less engines than the full set. And if you think of the Saturn V, if one of those engines failed immediately after launch, boy, you're in big
It
trouble.
wasn't getting to orbit.
You're in big trouble.
Yeah.
So that's the kind of things you have to watch out for. So the Starship is designed, it can lose a couple of those engines and still make it, into orbit, essentially, when they start flying there. Of course, right now it's suborbital flights. Now, so that's one nice advantage. Like you said, though, it's, you have to have everything lighting up right. You don't light them all at the same time. So it's
Right.
not
There's
like
a sequence to it.
there's a sequence, because that puts a huge amount of stress on the vehicle if you have all 30 some plus engines lighting up at once. That's a real kick in the pants.
Yeah.
So you want to kind of
You
minimize.
could say that.
Yeah. To minimize those stress, of course, you could have several of them lighting up. And I'm sure there's a way of optimizing which light up first in terms of the stress and strain on the vehicle. What's the proper sequence and all of these kind of things, right? And things are shaking
Yep.
and moving. So we have the technology. We can understand that today.
So, I will also point out the Soviet Union back in the day were using uh, liquid oxygen kerosene engines, whereas we were using liquid hydrogen, liquid oxygen engines. So that made a big difference
But
too.
but not for the first stage of the Saturn V. That was kerosene and liquid oxygen LOX.
It was kerosene. I didn't
Yes.
know that.
Yeah, the F1
Okay.
engines ran on kerosene and liquid oxygen. It was the upper engines and that went to liquid hydrogen and liquid oxygen.
Okay. Well, that kind of makes sense too. The less hydrogen you have hanging around, the better off you are.
But of
That's
course,
for sure.
and nowadays, of course, the fuel they're using methane,
Methane. Yeah.
and that's more stable and easier to handle than some of the cryogenic type of stuff, right? And
Right.
anytime something is easier to handle, you know what that means? It's cheaper.
Yep.
And remember, the goal here is well, number one, it's not a government-run entity. It's a private company, SpaceX. And so their number one goal, like any company, is to make money, right? Turn a profit
Right.
eventually. So you're trying to optimize things to maximize your profit. And that's one of the decisions that was made early on. And the use of methane is not unusual. Other countries are doing that too. And you get a nice bang for the buck in terms of
Yep.
specific impulse. Not quite as good as hydrogen, but then you don't have all the problems that you have dealing with such a cold, material.
That keep in mind, you are still dealing with liquid oxygen.
Mm-hmm.
because you don't have to, but hydrazine is almost as bad, if not worse in ways. But you've got to have an oxidant, an oxidizer.
Yeah.
So you are taking some nasty stuff up with you, no matter what you choose to use as the main fuel, the main propellant.
And even like the V2 rockets from the Second World War, they ran on, if I'm not mistaken, fuel would be like gasoline, and the oxygen source was liquid oxygen.
Mm-hmm.
So even from the early days of liquid propulsion, LOX, the liquid oxygen was the main oxidizer.
Right.
Now, on this slide I'm showing is a beautiful image taken from a camera on board the rocket part, that first stage, as it's separated, moving away from the top, which was the ship part, the one with these 6 engines, the one that would hold the cargo. And you see this beautiful view with the Earth in behind, sort of thing. I mean, this is just beautiful. I mean, this is a picture to make a poster out of, right? It's so nice.
Oh yeah.
It's just it'd be amazing, to see this view, firsthand type of thing. But yeah, so the idea then is the part of the top half of the stack, if you like, which contains the 6 engines. These are just suborbital flights, but eventually, even on it's not the next one. The next one, they're going to go around once, I think, and then come back. But we're talking about getting really close to the time when SpaceX is starting to put these things into orbit. And
Yeah.
it's such a huge amount of cargo that you can carry in one of these vehicles. It's amazing. And of course, a version of it is going to be used as a lander for getting people back to the moon. So we can see how all that plays out.
Absolutely.
So the vehicle itself, thinking about what went wrong on the flight last week, the bottom or lower stage of the rocket was due to fly back and make a soft touchdown in the ocean. It did fly back. It did start to do a soft touchdown, but not all of the rocket engines lit up. They were supposed to light, if I remember right, like 13 engines out of the 30-some that are there on the bottom, the first stage. And that didn't happen like it should have. And so it hit the water a lot harder. And of course, it tips over. And then as soon as you hit the water, it blows up because the tanks rupture and so on. And you got a source of flames there. And so that didn't work out. The idea is eventually bring that back to the launch pad, and like they done before with the chopsticks, and grab a hold of it.
Mm-hmm.
In fact, eventually the upper stage that would go in orbit, that would come back later too. And once again, that would be grabbed by the chopsticks as well. And the goal here, of course, is to make it fully reusable.
Yeah. Because the more you don't have to make from scratch, the cheaper it gets.
Yeah, exactly.
So, yeah.
Now, thinking about the ship itself, the upper part, the business end, if you want to think of it that way, is that did its thing, right? The engines fired a nominal length of time, and I think the V2 was ethanol alcohol. Yeah, it could have been alcohol. Zoho mentioned it, and LOX was indeed the oxidizer. Yeah, I was trying to remember. Of course, I wasn't around back then, but you read all about it in the history of rocketry with von Braun and stuff. So it's interesting. People in London didn't like them too much, but I mean, in terms of the rocketry and advancing, space exploration, it was definitely a stepping stone in the right direction for how things eventually played out. But the ship itself, its engines, 6 engines fired the nominal length of time. And in the past, that hasn't always happened. They stopped short because of various issues. We even had one explode, like disintegrate, so that was lost. Yep.
Unscheduled, rapid disassembly.
Hey, we're paying by the second on this podcast. We got to use shorter words.
Oh, okay.
Get to the point. So, and this time it did its thing. It had coasted around the Earth, essentially, in a suborbital flight. Made it all the way to off of Australia a little ways. And then it flipped over and did this nice soft touchdown on the water. In fact, the touchdown was so soft, it actually stayed buoyant for a considerable period of time, so that you were able to get some good, views of it. And the SpaceX knew it was going to land, and they had a drone standing by, taking wonderful pictures of the underbelly of the ship in order to get an idea of how the tiles for reentry through the atmosphere, how they fared. And you can get some really important engineering data. And they did a great job, right? So I remember, lots of these flights, the fins would burn off and different burn throughs on the structure itself and so on in the early days. But they've really perfected this technology, SpaceX, and it's just looking better and better all of the time. So it's going to be amazing, to see what they end up doing. So here's a close up at the engine end of the ship while it's resting on the water, and you can see 3 smaller engines in the middle and the larger 3 engines ringing the outside. And it's just floating in the water. And I thought, once it hit the water that it would just go under pretty rapidly, but no, that's not the case. It was pretty well sealed. There was no burn throughs or anything like that, and so it floated for quite a period of time. So really cool. They really got this technology heading in the right direction.
Excellent. That's good to hear. Yeah.
I mean, people might wonder, why are you going off the deep end for this vehicle? And it's a SpaceX private company. Elon Musk has enough money. He's the world's first, trillionaire or whatever it was, at least for a while. That's how the stock goes up and down, and now it's been down a little bit. But, well, I mean, this is important because it's the direct tie-in with what's happening with our return to the moon and how long that's actually going to take in terms of the Artemis project. The next Artemis flight, and they're assembling the rocket now, the next Artemis 3 mission is supposed to test either the SpaceX lander, which is related to the technology here, the Blue Origin lander that they're currently building, or a combination of both of them, ultimately, resulting in Artemis 4 landing on the moon, and with one of these landers that they decided to use. So it's all tied in, whether you like it or not, with what's going on with the Artemis project and ultimately human return to space, back to the moon, and on to Mars. So, 100 years from now, when you write the history of the space age, SpaceX is going to be there front and center, no matter who runs the company.
Yeah.
So.
No, I agree. I'm one that hopes that Blue Origin and Boeing are right there with them, but who knows what's going to happen with Boeing.
Yeah, they have a lot of issues, and
yeah,
to get their vehicle up again, there's going to be a lot that needs to happen, unfortunately, with Boeing. So there's even talk they may even just abandon it, lost cause in that sense, but who knows? They have something there. I don't know what happened, right? That they had run into so many issues with the thrusters and all these type of problems, whether it was like subpar testing or it was money issues that you're trying to do a lot more with less than what they should have. I don't know. I mean, I don't know if people really fully know what's going on. Maybe Boeing doesn't themselves. Who knows? Eventually we'll find out all that information. But
in the end, I'm reminded of a quote from a movie. I won't name the movie, but one of the guys in it just starts spewing off on how American components, Russian components, all made in Taiwan. Yeah.
and then a
lot of times that's what you're dealing with. So,
and of course you got to add in if a government contract is the lowest bidder to the government, right?
Right. That was kind of his point,
Yeah. Well, we'll see how this plays out. It's amazing technology, and it's a wonder how far back in time could we have accomplished this? Could we have done all of these things in the 60s if we wanted to?
Right.
And
I think the answer is maybe.
You're riding the fence on that one, eh, Robert?
Yeah.
Well, the way why I say that is because if a lot of the stuff would have been developed back then and utilized, how do you know where we would be today here in 2026? What would be our rockets look like now?
Right.
But it seemed seemed like there was such a, and correct me if I'm wrong, like a tail off, if you like, or our attention was turned elsewhere for a long period of time after the Apollo project. And a lot of this technology wasn't developed further or developed as much as what it could have been.
Right. That's pretty much exactly what happened. We went from, space exploration and rocketry being a priority to, we've been there, we've done that, and public support and political support were dried up and the funding dried up. And here we are trying to get both back, or all 3 back.
Yeah, I mean, the big push was what, 50 years ago, when they landed Viking 1 and 2 on Mars.
Yeah.
And that kind of got that going a little bit. You know, it didn't happen right away, but it wasn't that long after that we started getting this idea, okay, let's go to Mars and let's search for the water, you know, faster,
Yeah.
better, cheaper. And it was all these different buzzwords that NASA had invoked under different, you know, administrators through the years. And the
Hmm.
end result of that, and it takes a while to ramp up the, you know, these different technological developments and then get it all approved for launch and launching it. And the actual transit time from Earth to Mars is like relatively minor compared to all of the prep work that goes into it, how long it takes, raise the funding and all that kind of stuff. So we end up with rovers on Mars. And just to kind of give an example of that, here's a beautiful image that was released just a few days ago of one of the wheels on Curiosity. That's a rover that's on Mars. It's actually been roaming around on the red planet for nearly 14 years now. And you can tell from the condition of its wheels, it's been there a while.
Yeah.
Boy, Robert, if you had a
How,
car that had a wheel like that.
yeah, but how many wheels do you know that you can run for 14 years, you know?
And on the surface, right? It's not like the
Right.
surface is smooth, right? It's got all these jagged rocks, and, you know, depending on the exact terrain that you're running it across, it's not all like beautiful fine-grained sand or something that you're running across. There's some sharp, jagged rocks, you know.
Hmm.
But
And the next generation of rovers, that's one of the things they're trying to develop and implement, is a different type of wheel that will be more robust, you know, last longer on those rugged conditions, but also be lightweight. And you get the idea.
you know, that stuff was worked at back in like early 60s before we landed on the moon.
Hmm.
Because don't forget, we had the rover on the moon as well,
Yep.
and they were
The moon
looking,
buggy.
and yeah, and they were looking at the different wheels and what could absorb, you know, impact of large obstacles when you roll over them and all this kind of stuff. And so it's not new, right? It's been something that we worked on for a long time for different sort of situations on the moon, and then thinking about what we do when we get to Mars. But boy, Robert, if your car was like this, you'd be hard pressed to get to your Walmart store.
Right. In fact, I don't think I would. I think I'd get some support jacks, bump it up, take off 2 tires, get a friend to take me to Walmart or wherever, and get new ones put on, bring them back, jack up the other end.
Well, you just gave me an idea. Why can't we have a couple spare tires on this rover, and we have a robotic arm that just replaces them when they need to be replaced?
Yep. And now you're getting into a whole new type of, the stepping stone to the Van Neumann type probe,
Right.
where it's got the programming and the machinery to duplicate itself.
Yeah, that'd be interesting if you could do that. Or
Absolutely.
when the rovers were designed and put on Mars with these type of wheels, we didn't have a full understanding of what the surface was like.
Hmm.
And it's only when you actually go there in situ, right, and make these type of measurements and see what's actually is the different variety of landforms that we encounter, then you can go back and say, okay, let's redesign these wheels so that they can better stand up to the environment they're going to be exposed
Hmm.
to. And I think that's going to happen for future rovers. We'll definitely be doing that.
Yeah. There was a lot of that happened back in the Apollo days, because people were absolutely floored by how toxically sticky the moon regolith was. I mean, but then when they got it under the microscope, because it's essentially, just spiky glass balls.
Well, now you open up a can of worms. Think about that, right? You look at all the footage from the Apollo project, and you see the astronauts covered with dust, lunar dust.
Mm-hmm.
Then they go back into the lunar module, and let's say it's one of the later missions, so they actually have an opportunity to go to sleep, and then they get up and go back out for another roam around, EVA. And in the whole time that you're in the lunar module, they were complaining there's dust on everything. And how much of that
Right.
dust goes in your lungs, and it's made up of these little pieces of glass particles.
Yep.
What kind of damage would that do to your lungs over, long exposure?
Ask a coal miner
So it's
because it's
not
a
good.
similar situation.
So in that sense, you'd have to put a filter over your mouth immediately and nose so that you
Hmm.
minimize breathing in these particles that are going to be, moving around in the lunar module while you're on the moon. There's some gravity, but I mean, those particles are not going to settle out, just like on Earth when you can blow across the surface of a dust surface or something, you see it all flying up in the air. How long does it take those little dust particles to settle down back to the ground?
Right. And the lunar gravity is lower. And one thing though is that there is no air to give it a terminal velocity, so it's going to fall faster than it would in air. But
No, well then you're inside the lunar module. Remember, it's
oh,
pressurized.
right.
Yeah.
Okay, I thought you were talking about outside.
No, when you're taking off your helmet,
Okay.
you're going to sleep for the night. You're breathing all that lunar dust
Oh
in your
yeah.
lungs.
No, it's going to linger. It's going to drift.
Yeah, so it's a good
Absolutely.
lot of that's going to go down, and so I don't know if they wore a mask like that to filter it. I don't never seen any images or pictures taken inside the lunar module that showed that,
Right.
but it would be worth thinking about.
Well, I think they're trying to develop suits where there's, bottom line, you slide into the suit never comes into the hab,
Yes, a sort of
and
a
you
docking
slide it.
port.
Yeah,
Yeah.
you slide into it, disconnect, and now go wandering, so that stuff never gets inside in the first place because it's nasty stuff.
Oh yeah. And what does it smell like, Robert? Do you remember?
A gunpowder.
Yeah. So imagine that. I mean, gunpowder is unique. You got that sulfur type of smell to it. But
Mm-hmm.
if you imagine smelling that continuously for hours after hours
Yeah, right.
when you're sleeping or trying to sleep.
But I got to admit, maybe one of these days I'll remember and actually look into why it smells like gunpowder, because it's not that there's a lot of sulfur on the lunar surface. It's primarily andesite and basalt.
Yeah.
And those minerals don't, or rocks don't have a lot of sulfur or other components that should smell like gunpowder. So it'd be interesting to find out why. I might have to write me a note about that. uh, so yeah.
Well, I'm just checking to see if I can find that information in real time here.
Oh, okay.
The beauty of the internet.
Right.
Let me see what
So
it said here.
I guess I can keep talking while you're looking that up. But uh, even if we learn how to go further and we get to Mars with boots on the ground, these are the same types of things we'll have to think about there, because Martian regolith is going to almost certainly have its own problems. Mars has a atmosphere that tumbles the stuff around, and it's going to round off a lot of those spikes and points and everything. But I can guarantee it's going to have its own set of problems that we're going to be surprised by, and we're going to have to figure out how to deal with.
Okay.
But that's what we do, humans.
Now, here's an interesting. I'm glad I looked this up. This is very interesting. You ready?
Okay.
The smell of fireworks or gunpowder for the lunar regolith or lunar dust is not due to the makeup of the rocks or dust itself.
Okay.
It's due to the volatile reaction when you expose the rocks and dust to an oxygen environment inside the lunar module. Interesting.
Okay.
There are unpaired or dangling bonds of electrons on the surface of the dust. And they oxidize, they make bonds with the oxygen in the air inside the lunar module.
Mm-hmm.
And at first it gives off that rapid reaction that occurs, gives off the scent of the gunpowder like smell. Once you bring the dust particles back to Earth, they don't smell. They don't have an odor. So people on the ground, the scientists who received that material, couldn't smell the gunpowder smell. It was only when they're first exposed to an oxygen environment do you get a release of that odor.
So the rapid reaction between oxygen and the iron, probably
Yes.
iron and potassium,
Yep.
uh,
Iron and silica.
create, yeah, creates volatile chemicals that's what you're picking up with your nose. Okay. No, that
Yeah.
makes sense.
Yeah, that's
Yeah.
interesting. So it's just a sort of just a thing that happens and then it goes away. It's not a continuous sort of thing because it's not. So it's not the elements that make up the rocks, right? In that sense.
Right.
So that's neat.
Neat. Yeah.
Just to show you that it's not just the one wheel on the rover that has issues. Here's some images of some of the other wheels, and they all maintain major damage, as you can see, which is what you'd expect. So I don't know how long these rovers could go for before you. What do you got your money's worth out of the Curiosity rover? That and you government officials say, how do you know that? Because we drove the wheels off of it. Is that what you're supposed to say?
Yeah. Well, let's face it, Spirit and Opportunity were designed for 90-day missions and ended up going for what, 7 years?
Yeah, something like that. It was unreal.
So these rovers are always heavily over-engineered. And it's because NASA wants to get that 90 days or that 120 days. The little helicopter that was recently up there finally died, but it was like months past its operational, yay, the mission worked, deadline.
And
So
the Curiosity is nuclear powered.
I didn't know that, but
Yeah.
it has an RTG on it.
Yeah.
Cool.
Just like Perseverance. So this is the first main rover that had nuclear power and doesn't rely on solar panels. I'm just thinking now of Marty McFly saying, this sucker's nuclear.
Right?
Back to the Future reference. Now you know how old
Yep.
I am.
Yeah, we won't go there thinking about, if that was being made nowadays, how far back that would mean.
Right.
Yeah.
Yeah, amazing, right? But anyways, I'm sure all of this will creep into the next designs of rovers as when we get to that point and see a lot of changes to make them better and better and better. I like to make them more and more and more in terms of the number of them.
Yes.
Without having to spend, the U.S. Treasury on them or something. Right?
Yeah, because no offense, as glamorous as putting boots on the ground is, and I will never decry doing that, folks, you get a lot more science out of the rovers.
Well, I mean, it depends, right?
It does. It does. A rover is not going to pick up, hey, what's that weird looking rock? As readily as a human geologist would.
And of course, we had experimental drone helicopter-like device on Mars already, proven that it can fly in the thin Martian atmosphere. So let's make lots of them, and let's have them go to very interesting places like Valles Marineris, which is isn't that like 10 times larger than the Grand Canyon here on Earth?
Something like that.
And you could fly down the throat of Olympus Mons, right? The extinct volcanoes, giant shield-like volcanoes like Hawaii volcanoes on Mars. So you can go down inside them and look around and see what's there. You can have all kinds of interesting places you can go. And of course, you'd have to send them to Cydonia, where they have all that structure there, according to some people, the face of Mars and UFO remnants and all of these things, right? And bring some of that back, Prove us all wrong that there are UFOs.
I was about to say, except MRI has kind of thoroughly mapped that section. So.
Ancient technology, that life grew on Mars first before it came to Earth and all this stuff, right?
Yeah, maybe.
Now, thinking about what can happen in the future, I thought this was a quite interesting paper that came out recently, and it's concerning a wandering black hole. And that seems like the most god-awful way, no pun intended, of worrying about what's going to happen in the universe. As you worry about not only are there black holes, and you might wonder, would the Earth ever go near, that is the sun, would they pass by in the future near a black hole? Is that possible? Well, what about, are they wandering around the universe, these black holes? And for some unlucky star, it gets too close to the black hole, of course, the major problem there. So are there even wandering black holes? Or are we talking about black holes that are really massive, millions of times the mass of our sun? Are these black holes confined to the center region or the nucleus of galaxies? And as long as you stayed away from the center of galaxies, then you're not going to find yourself exposed to these millions to billions of solar mass black holes. Well, there's been a recent event that has been observed called a tidal disruption event. And there have been hundreds of these things have been cataloged over the last many years. And what they are is when an object like a star passes in front of a black hole relative to us. And I don't mean like there's a large distance between the black hole and the star. I mean literally that the star is just outside the event horizon of the black hole itself. So the curved space-time in the vicinity of the black hole will have an effect on the actual structure of the star itself. So you can get gravitational effects occurring, tidal forces where material can be stripped off of the star and so on, depending on, of course, the mass of the black hole and what is the extent of the curvature of space and time around it, where the star happens to be. And some of these stars can get awfully close to the black hole itself. And so we at least think that some of these tidal disruption events are due to this close passage of mainly stars in front of a black hole relative to our point of view. And one of these events was observed last year, and it's in a galaxy that's about 671 million light years away. So, Robert, this is not something you're going to go visit next weekend.
Speak for yourself. I'll be there tomorrow. Sounds like a great vacation spot.
Unless you're doing some remote sensing with your telescope, right? With a large enough telescope, you'll be able to see it.
Yeah.
But what we think then is happening with this is that the black hole that's ultimately responsible for one of these TDEs, as we call them for short, is not at the center of the host galaxy. It's actually on the order of 30,000 light years from the galactic center, from the center of that galaxy. And in this slide, I show you some images that were taken in the optical. There is two of them on the left side, one above and one below. And the one that's below, you can see the circle there and the object. You can actually see the brightening up or the flash of light coming from the location and where we think this black hole is located. And then there's a zoomed in, if you like, image on the right side after the light has faded away, showing the galaxy and where that event occurred. And it occurred, notice, not at the center of the galaxy, but in our way we got things set up here, off to the right side. And if the object is in that galaxy, that is at the same distance of the galaxy itself, then the distance from that circle on the right side to the center is about 30,000 light years. Now, the interesting part of all of this then is let's look at detail about the physical feature of this object. So one of the things you can look at is the light curve, and that's what we're showing in this slide. So what we have is really the brightness of the object that's plotted on the vertical axis versus days before and after the peak emission, the peak brightness that I showed in the previous slide. So on the horizontal axis, on the left side, you see negative values, and these are in days. So that's days before the peak of the brightness of this event occurred, which is in the middle as it's laid out. And then on the right of the zero vertical line, those are days after the event occurred, so post tidal disruption event. The data points are taken in various filters. There are ultraviolet filters, there is a sort of a bluish filter, and there's a red filter, and there are some infrared filters on there and so on. And the data points that you see plotted here then represent, starting from the left going towards the right, an increase in the brightness till you hit the peak, and then a decline in brightness. And it turns out that these are extremely important because it gives you information that you can use to constrain the models of what's actually producing the flaring up in brightness of this object. And based on everything that we're seeing in the different wavelengths, it is totally consistent with one of these tidal disruption events. It's not like a flaring active galactic nuclei or something like that, but it's consistent with it coming or being produced by a black hole with a mass of around 1 million times the mass of our sun. So 1 million solar
Oh my.
masses. Yeah, and that's interesting, and I'll explain why here in a second, but just to remind you, one solar mass is equivalent to about 2 times 10 to the 30 kilograms. So this is 1 million times that number.
So add another 6 plus 6 on that exponent.
Yeah, 6 orders of magnitude greater. Now, the thing is, in the outskirts of galaxies, like our own Milky Way or an elliptical galaxy or whatever, you wouldn't expect these really massive black holes to exist. These black holes have been found in the center regions of galaxies of this mass and greater, but not in the outskirts. So if we see any black holes, like the nearest black hole to us, for example, if I remember right, it's on the order of like 1,400 light years away. It's on the order of a few times the mass of our sun, right? The largest of them, you're up to like maybe 30, 40, 50 times the mass of our sun. And a lot of those values now are more well constrained today than they were 20 years ago, because we can detect gravitational waves from the merging of a lot of these systems. And those waveforms that we detect with LIGO directly correlate with the progenitor. What are the objects that are actively merging? What were their initial masses and their distances and so on? And we know a lot of these gravitational wave detections are caused by the merging of binary black holes of tens of solar masses, approximately on average, right? So we just don't see the massive ones like we're talking here, like millions of solar masses. They don't seem to exist, right, in the outskirts. They seem to, like I mentioned, they seem to be found in that deep potential well of the galaxy itself, in the central regions. But what's to stop some of these to wander, to be ejected from the system, maybe in different, three-body encounters or whatever you can think of, where some of these ultimately got, flung out of the system, or maybe mergers with other galaxies early on, billions of years ago. And some of these, even though they have 1 million solar masses, occasionally one of them will get ejected from the system and out it goes. And if you allow it to wander around for 1 billion plus years, eventually it's going to be 30,000 light years from where it started from. So that's, yeah.
That was going to be my question, and you've answered it. Was this event a stellar mass black hole, a few tens of solar masses tops, or was it a supermassive? Because a supermassive being that far from the center, okay, I'm nervous.
Hence, getting back to what I mentioned about, some people are scared, and you can write a nice sci-fi story about this, about the wandering black hole that came too close to the sun and our solar system.
Yeah, that's a little unnerving, because, a stellar mass black hole coming close to the sun, depending on how close it got, we might not even notice it was there. But 1 million solar masses? No, that passes in the neighborhood, and it.
Well, the worst thing would be, of course, is the disturbance of the orbit of the planets, including our own Earth.
Right.
What would
Not a fun prospect.
Well, how would you even fix that, right?
Well, you couldn't.
The Earth all of a sudden goes on a dramatically elliptical, highly elliptical type of orbit. Life as we know it no longer exists on our planet.
Right.
Or which is less, and that's the most likely scenario, probably, if not ejected out of the solar system altogether or sent towards the sun. I mean, the other possibility, which is a much, much less of a chance because space is so large compared to the size of our planets in our solar system, is you somehow get on a collision course with another planet that crossed our orbit at the same time we were there with them, type of thing. But
right.
the altering of our orbit, even a little bit, it doesn't even have to be dramatic if you think about it, right? The Earth is almost in a perfect circular orbit, not quite, but pretty close. I mean, so close, in fact, that if you ask the common person who doesn't really know a lot about astronomy, when is, and you're talking to somebody in North America, when is the Earth closest to the sun? And you know what they're going to say? Oh, in the summertime.
Right.
And that answer is wrong, right?
Yeah, we're furthest away in northern hemisphere summer.
Yeah, and we're closest the first week of January to our sun, but it doesn't feel like that, especially if you're in Grand Forks,
Right.
right? In early January, you're not going to say just from your senses, and that's because the difference between when we are the closest in January and the furthest in July is so small. The tilt of the Earth's axis and the different seasonal effects we get from that overwhelms that difference in distance from the sun.
Right.
But if we end up being on a slightly different orbit where that difference becomes significant, look out.
Yeah. Because we're burning up at closest approach and freezing out at furthest.
Now,
Yeah.
and think of this to go along with the idea of this wandering black hole. It's number one, it's about 1 million solar masses. But if it started out, as you suggested, let's say you had a 10 or a 20 solar mass, so it's more easily kicked out of the center of the galaxy to make it wander, how did it accumulate all of that mass? If you're
Right.
comparing 10 to 1 million, you may as well say it's right? There's no comparison there at all.
There is no comparison.
You need
The
so
10
much.
mass doesn't matter.
Exactly. It doesn't matter compared to 1 million. So it probably started off with a large amount of mass, probably close to 1 million. So what event, and we're talking like mergers of galaxy type of events that could force then a 1 million solar mass black hole to be kicked out of the center region of what ultimately would form the single galaxy, which would be the end result of this merging process over, probably several billion years.
Yeah. Wow.
Yeah, and this is actually the first real good sort of case that we have with this type of these, tidal disruption events occurring in the outskirts of a galaxy. And of course, immediately my thought on all of this was, for example, are we really looking at the galaxy itself? How do you know that
Right.
event didn't occur in a very low mass galaxy that's near the larger galaxy? Maybe it's in orbit around it, just like the Magellanic Clouds are in orbit around the Milky Way. How do you know that event didn't occur from a galaxy like that? So it did not get ejected from the larger massive galaxy that we can easily see in those images. How do you know it's not from a dwarf galaxy that's really faint? Well, of course, you look with the largest telescopes that you can get, take deep imaging, long exposure time to try to resolve or see any type of enhancement of that location. So if we go back to, let's say, a couple slides, so this slide here, showing you the circle, you look carefully in the interior of that circle. Can you make a case? Can you make an argument that there you see some sign of another galaxy? It could lay, in front of it relative to us or in behind relative to us. Is there anything there? And the scientists who analyze this data and publish this paper, they don't see any sign of another galaxy down to some very faint magnitude limit. So it doesn't look like it's there. And the other thing you got to worry about is there's this beautiful correlation that we have between the mass of the galaxy and the mass of the black hole. So black holes these supermassive black holes that tend to be more massive reside in more massive galaxies. So you can use that correlation, and there's some scatter to that correlation, so you don't get exact values like most everything. But you could take the 1 million solar mass black hole and use that correlation to then estimate what would be the typical mass of the galaxy that it should reside in. And you get, therefore, an estimate of its mass, and along with that, its luminosity, its intrinsic brightness. And what you can say is, if it's at the same distance as this larger galaxy nearby, it should be visible given the quality images that we have. And it's not.
Mm-hmm.
And it's not. So it's either in a galaxy that's much, much further away, or it is an isolated black hole that came from the center of the galaxy that we see clearly in these images. That's what you're left with. Well, of course, you want to do more than look at images and measure the brightness of things. What makes astronomy astrophysics, Robert?
Is spectra.
Spectra.
That's where the rubber meets the road.
Exactly.
Because Yeah.
What
So
kind of physics do you get out of spectral analysis?
well, you get fingerprints of what elements are involved. You get are able to analyze things like surface gravity because of the broadening of the lines, those peaks in those colored curves, and the shape of that broadening gives you indications of the rotation of things involved. And yeah, spectra is better than any fingerprint on a person by just yeah. There's really no comparison. Spectra tells you the underlying physics of what is going on in this scenario.
And they've acquired spectral data, which is what's displayed here on the slides. The individual spectra are offset vertically so that you can better see them rather than pile them on top of each other and you wouldn't be able to see anything. And what you see is at the very top is prior to the event, and then going down as you go post event and many days afterwards. And you can actually see, I mean, this galaxy has been mapped before, right? And we have spectra of it before the event occurred. And so you can actually see the spectral evolution that occurs over time as this event reaches a peak and then the light falls off again. And it's interesting what you notice. For example, you see definite evolution in both the lines that represent hydrogen and helium. Mm-hmm. And what this really gives you then is model testing. You can take these detailed spectral changes over time and then apply it to your models and say, okay, for example, will an active galactic nuclei explain these spectral changes as well as the light curve and the photometry that we showed in the previous slide? And you can pool all that information together. And when you do that, the most reasonable explanation that we have, given the data at hand, is that this is definitely one of those TDE events. And that therefore it would be a black hole that ultimately would cause it. And the black hole to give rise to the effects that we see then is once again on the order of about 1 million solar masses.
Yeah, I'm buying it for another reason that may not be readily obvious. I'm looking at the time evolution and watching the scatter on the data increase and then decrease back down. It's kind of like you drop a rock in a pool and then drop another rock nearby. For a while, the noise goes up from both ripples, but then as it evolves, it dies back down. So this is a disturbance event. Yeah.
Now, if you find one of these things, you know there are many more out there that we just didn't recognize. So it'll be interesting over the next several years if we can find some more of these, TDE type events that are occurring for a progenitor that's a black hole that's far away from the center of the host galaxy. That's kind of sums it up in that. And that just makes it interesting. You never know what's out there lurking around in the shadows of the night, Robert?
There you go. There was a theme song from a show that talked about the shadows in the night, wasn't it?
I'm sure there's been lots. I'm sure somehow it's related to like vampires or something.
Oh, yeah.
Or werewolves or...
Blah, blah.
Anyways, that's another hazard, right? When you're out in space, flying around in your Star Trek interstellar spaceship, you got to watch out to running into black holes.
There you go. Good old Han Solo talking about about precise calculations. You'll find yourself in the middle of a star flying into a black hole, and that'll end your trip real quick.
Yeah, I think I'd be more worried about that, but space is so big. Even if you did a random location and distance from
you're probably in empty space.
Yeah, exactly. So maybe you don't have to worry about it so much.
Yeah.
Right? Anyways, but if you're interested in all these kind of things, of course, what would happen in the future? How is this research going to evolve? What we're going to learn from it? How does it make gasoline cheaper at the pump? All these relevant things, right, that people like to look at. One of the things you can do, of course, is get yourself educated. And it doesn't matter how old you are. Even if you seem like you're finished your main career in life, why not start a new one? Right? You're
Absolutely.
never too old to learn new things. And you can do that, of course, by coming, for example, to the University of
North Dakota.
North Dakota. We have lots of programs here, lots of courses that you can take for fun or just to get a new career going or whatever it is, both online and on campus. And we have lots of construction right now going on campus. We have a new STEM building that's going up and up and up, and you see significant changes almost every day. And so you can drop by and have a look at that, and of course see all kinds of interesting things. And in a few more weeks from now, everybody will be back on campus.
Right.
And that's always...
It's almost the new fall semester.
It is, and that's a real exciting time, in the year. I always find it better even than when students all come back in January after the Christmas break, because they've only been gone for like a few weeks or so. I find where you get that much, like 3 month off in the summer for students, when they come here, it's like a whole new group, which it is, so many new freshmen just coming back, first year students. And there is a real buzz, on campus when that happens.
It's definitely a different energy.
Yeah. That's really, really neat. So come here to the University of North Dakota, and if you can't make it, like I said, physically, nowadays it doesn't matter. As long as you have a computer that you can log into, you can take classes online, and we have lots to choose from. There's not just a few here and there. It's pretty substantial. So please check that out.
Absolutely. Yeah, come join us.
Come join us. Now, Robert, our next podcast, which we advertised at the beginning, is next Tuesday, August the 4th, where we're going to have our special guest, Seth Shostak from the SETI Institute will be here. Yep. I'm sure we'll get into a real in-depth conversation, a lot of interesting stuff. How do you find life elsewhere? What's the chance of life growing, civil, intelligent life, as we like to say, elsewhere, which is completely different for the chance of, like bacteria type of things growing. We want intelligent life, something that can build radio telescopes and send rockets into space, this kind of intelligent life.
Right.
That's what we're looking for.
That's the neat stuff, at least in my opinion. I mean, finding microbes would be neat too, but
long
being able to talk to somebody.
And of course, long as it's not like the Borg.
Yeah, that we don't want to find that.
We don't want them to know we exist, at least for
or
as long
the
as possible.
cyclos or any number of other less than. Yeah,
exactly. Now, we always leave you with a quote at the end of our podcast. So since we talked about Mars, Curiosity Rover and so on, and talked about space program with SpaceX stuff, I thought I'd bring up a quote from Wernher von Braun, and we actually talked about the V2, so it's rather fitting.
Yeah.
So this is part of an excerpt from an article that he published back in the mid-1950s. So it's the April 30th edition, 1954, of Collier's magazine. Now that magazine no longer exists, but von Braun actually published a lot into that magazine to try to promote the space program. Really, ultimate goal is how can I get the government to get interested in this enterprise and cough up the money that we can eventually put men on the moon. That was the idea, of course, and then go on to other things like Mars and so on. And so von Braun always had this wish then that ultimately we'd end up on Mars someday. And he even gave prediction of when it would be so. And it's interesting that his prediction, which I'm going to read a bit of it in a second, said that essentially in about a century from now, so that would be roughly in 2054, that we'll be ready to go to Mars and, on the moon and on the Mars and so on. He wasn't far off the way it's going. So that's about right, So here's the quote. Will man ever go to Mars? I am sure he will. But it will be a century or more before he's ready. And that time, scientists and engineers will learn more about the physical and mental rigors of interplanetary flight and about the unknown dangers of life on another planet. Some of that information may become available within the next 25 years or so through the erection of a space station above the Earth, where telescope viewing will not be blurred by the Earth's atmosphere, and through the subsequent exploration of the moon.
Nice.
And that's
He was a
actually
pretty sharp
came to
fella.
yeah, pretty dead
Yeah.
on in those predictions, for example. Very good. Very good.
Yep.
Now, of course, with that, we're ending the podcast. So thank you very much for watching and joining us. Don't forget, we'll be here next week with our guests. And bye for now.
Bye, folks.